At this point, you should be pretty comfortable with relating objects to one another through something called inheritance. Let's look at a basic inheritance tree. Let's say we have something called a vertebrate at the top, and then we get more specific as we go down the inheritance tree. We know that we can create a new cat object where the reference type, meaning the thing on the left, is the same as the object type, the thing on the right. So we can have a cat equals new cat. But because of inheritance, we can actually make the reference type, or on the left-hand side of the equal sign, more generic. So we can have a fish of new salmon or a vertebrate of new dog. The reason that we can define things this way is because we know through inheritance that whatever is up in a superclass is going to be guaranteed to exist in the subclasses. They're inherited. We know that you have that behavior. This offers some flexibility as we're defining our classes, but it starts to introduce us to this idea that maybe code behaves a little differently based on where we are in the inheritance tree. The idea that you can have the same method produce different results based on where you are in the inheritance tree is called polymorphism. Let's look at an example. Let's say we define two objects, both of reference type vertebrate, but one's a salmon and one's a cat. Well, when we call printinfo the same method on both of these things, we get two different results. That's because this method clearly relies on the state of each of those object instances, which is pretty cool. That same piece of code could do two totally different things. Let's look at this in implementation. At this point, you've probably noticed overrides, meaning you don't have to automatically inherit the behavior of a specific method. You can rewrite it and define your own implementation. Let's say we have an animal class that moves and eats. Here's a table to make it really clear what these methods do. If I have another object, say fish, that extends animal, let's say I implement my very own move method, and that has a different type of movement, swim. But I'm not going to implement anything else. I'm just going to let myself inherit from my superclass. That's what the green italic text means. It's not really there. I just get to use that functionality. Then I have a method behavior that looks like this, slightly different. That's polymorphism. Now we can have a sibling, say mammal, that also extends animal. So now these are fish and mammal are siblings. They're not technically related to each other, but they end up having pretty similar yet still different behavior. That's because in mammal, I can choose to override my eat class, but inherit my move class. We can go as many levels deep as we want. So if I have a cat that extends mammal, I can say override my eat class, but again, continue to inherit my move class. So my cat walks just like my superclass animal, but it has yet an even different implementation of the eat class. Polymorphism. Things get a little tricky when you start to inherit dynamic elements. Say, for example, instead of inheriting printlns, you're inheriting method calls. Let's start with our animal class that again has move and eat. Here is what would happen when you call the move method. Now let's make a mammal class that extends animal. I'm going to override move, and in my overridden move, I'm going to make a method call to a method called rest that I'm not going to override, meaning I'm going to directly inherit rest from my superclass. Now I have a new move method that walks, because I directly typed that out, and then sleeps, because I called my inherited method. So what if I create a class that then extends mammal, meaning it's now two away from animal, and I don't override move, but I do override rest? What's going to happen? Now when I call move, it walks because I inherit that from my superclass, but then I inherit not the println of sleep, but the method call to the rest class, which in my instance is nap. There you go, 3 different implementations of move. What about when you use the super keyword? Again, let's start with a pretty generic class. Animals, they eat plants. Sure. Here's what that method call would produce. Now let's say we have fish, and fish extends animal. I'm going to override my eat method. And the first thing I'm going to do in my overridden method is I'm going to make a call to my superclass's version of this method, super.eat. And then I'm going to add on the println of plankton. That means I'm going to look one above me and see exactly what my superclass produces. It produces the println plants. So that's what I'm going to print out first, and then I'm going to return to my overridden method, and I'm going to add on the plankton println. So what happens if I go one level deeper? Now I'm not overriding this method. I am just inheriting fish's version of eat. So who's salmon's superclass? As it turns out, super always refers directly to the class that you extend from. So when I'm running this method that I have inherited, I look to my superclass's implementation of eat, and that's what I use for my super.eat. It's plants and plankton. And then, because I have inherited that extra println of plankton, I add another one on at the bottom. So it's important to remember that super always refers directly to your parent, and it doesn't just go automatically all the way up the chain. That's why writing tables like this can be super helpful. Inheritance and polymorphism are incredibly powerful tools for relating your objects to one another and sharing code, but it can get tricky deciding exactly what's inherited and what's not. So sometimes writing out tables or using the debugger tool to know exactly what's going on is going to save you a lot of headaches trying to keep this all in your brain at once. Best to get a lot of practice and try as many different interpretations of your inheritance tree as you can, because if you can master this, then you can write some really well-structured code bases.